We've seen how the ideal gases obey several ideal gas laws, which are useful in making predictions about a gaseous system. But in order to make the math nice and tidy, we make a few assumptions in order to describe something as an ideal gas. These laws depend on the assumptions that the gas particles take up literally zero volume and that they do not interact with one another. But let's take, for example, a sample of carbon dioxide. These molecules do not take up zero volume. They are three-dimensional objects that do take up some space, no matter how tiny they are. And furthermore, we know that any substance is capable of participating in intermolecular forces. Even something non-polar like carbon dioxide is able to make weak dispersion interactions with other molecules. So if two of them pass by one another, they are able to very briefly interact, making their motion momentarily sticky, so to speak. Now, it's true that if the sample of gas is not at all dense, that is, if the molecules are spread out significantly, these factors are completely negligible, which is why the ideal gas equations work well for samples of gas that are roughly near atmospheric pressure and temperature. But imagine if we were to compress this gas. If we were to push the molecules closer and closer together, the space between the molecules begins to shrink, but the molecules themselves don't change. The molecules begin to run into one another more often, thus interacting more. We will eventually arrive at a point where we can no longer ignore these parameters. The volume that is occupied by molecules will become significant compared to the total volume, and the interactions being made by the particles will be substantial. When this occurs, we are dealing with a non-ideal gas. A non-ideal gas is what results when a gas is highly pressurized, which means that the particles are very close together. It is the fact that the space between the particles that has been reduced that makes their actual volume impossible to ignore. And at low temperatures, where the molecules are moving more slowly, the attractive forces between the particles are more difficult to overcome, so they will interact more significantly. So high pressures and low temperatures can cause a gas to display non-ideal behavior. Let's move forward and see how we can deal with this non-ideal behavior mathematically.